This video follows the notes, section 2.3b notes, polynomial and synthetic division notes, day 2. This video starts on the second page, which starts with synthetic division, and walks you through all the examples using my voice and shows you the answers to all the practice problems, but does not walk you through them. Enjoy. With synthetic division, just like with polynomial long division, you must order the polynomial in standard form, from the largest exponent to the smallest exponent, being sure to put placeholders if a variable does not exist. But with synthetic division over long division, you use the coefficients instead of the entire polynomial. So you write the coefficients in a line, and then you will end up adding down and multiplying diagonally. I will explain with the next example. To do synthetic division, unlike polynomial long division, you use just the coefficients for your polynomial. But just like long division, you must order them from the largest to the smallest and put in a placeholder if one's missing. So our polynomial is 1x to the 4th plus 0x to the 3rd minus 10x squared minus 2x plus 4. When doing synthetic division, you draw an L, and at the top part of the L, you do all the coefficients. So the coefficient for x to the 4th is 1. The coefficient for x cubed is 0. The coefficient for x squared is negative 10. The coefficient for x is negative 2. And the constant is 4. Now, outside the synthetic division is the 0. Since x plus 3 is what you're dividing by, and that's our factor, the 0 is negative 3. So that goes on the outside of the synthetic division. The first thing you do is you bring down the 1. Now you multiply the 1 by the 0. So you're going to do negative 3 times 1. And that number, which is negative 3, goes below the 0. So you have a negative 3. Then you add down. So 0 plus negative 3 is negative 3. Now I'm going to take this negative 3 and I'm going to multiply it by the number on the outside. So I have negative 3 times negative 3, which is 9. 9 goes under the negative 10. Now, the columns we always add. So negative 10 plus 9 is negative 1. Now I take negative 1 and I multiply it by negative 3. That's 3. 3 goes under the negative 2. Negative 2 plus 3 is 1. Now I take this 1 and I multiply it by negative 3, which is also negative 3. Negative 3 plus 4 is positive 1. Now these remaining numbers are the coefficients for my polynomial. Since it was a degree 4 polynomial, once we've divided, we go down one exponent. So since it was x to the 4th, our remaining polynomial is going to be x to the 3rd. So it's going to be 1x to the 3rd minus 3x squared minus 1x plus 1, and this one is a remainder 1. So to write this division, I have x cubed minus 3x squared minus x plus 1 remainder, what we divided by, which was x plus 3. Since this did not have a remainder 0, we can't factor it completely, but this is the problem divided using synthetic division. Here's another example using polynomial. Use synthetic division to divide f of x, 8 plus 2x to the 4th minus 4x minus 5x cubed by x minus 3. If the polynomial can be factored, factor completely. So the first thing we need to do with our polynomial is we need to reorder it. So this polynomial is also to the 4th, so we have to do 2x to the 4th minus 5x cubed. But we're missing our squared term, so we must put a 0. 0x squared minus 4x plus 8. Once we have rewritten our polynomial, we draw our polynomial L. Remember, the coefficients from the polynomial go at the top part of the L. So we have a 2, a -5, a 0, a -4, and an 8. Those are all the coefficients of the polynomial. Since x minus 3 is what we're dividing by, the 0 is just a positive 3. Remember, it's the opposite of what you have here. So on the outside, we have 3. Now remember, the first thing you do in synthetic division is you bring down the first number. So we're just going to bring down a 2. And then you take that first number and you multiply it by the number on the outside. So I'm going to take 2 and multiply it by 3, which gives us 6. The 6 gets placed underneath the -5. Now I add down. You always add down. So I have -5 plus 6, which is +1. Now I take that +1 and I multiply it by the number on the outside, which in this case is 3. When I do that multiplication, I get +3. So +3 goes underneath the 0. Now I add. So I have 0 plus 3, which is +3. Now I take the +3 that I got and I multiply it once again with the 3 on the outside. The 3 on the outside, when I do that multiplication, I get +9. That +9 goes underneath the -4. And now I have to add. So -4 plus 9 is +5. Now I take +5 and I multiply it once again by the 3 on the outside, which gives me 15. I put the 15 underneath the 8, and then I add. So 8 plus 15 is 23. Once I have completed my synthetic division, I remember that my original polynomial was to the 4th power. So my new divided polynomial is to the 3rd power, and the numbers down below are the coefficients. So my new polynomial is 2x to the 3rd plus 1x squared plus 3x plus 5, and my remainder is 23. So how do I write that in division form? Well, I can write f of x divided by x minus 3 equals 2x to the 3rd plus x squared plus 3x plus 5 plus 23 divided by x minus 3. This is my answer to the question if the polynomial use synthetic division to divide. The factor theorem states that a polynomial f of x has a factor x minus k if and only if f of k equals 0. So that means if your 0 is in fact k, and you plug in k into the original function, and you simplify, you'll get 0. The remainder theorem states that if a polynomial f of x is divided by x minus k, then the remainder is f of k. So if you take the k value and plug it into the function, and it gets you a number other than 0, then you have a remainder, and that is in fact your remainder. But if you take k and plug it in and you get 0, according to the factor theorem, then that is in fact one of your factors. To use synthetic division to show that something is a 0, you need to have no remainder. So let's do synthetic division. So since 1 is my 0, I'm going to put a 1 on the outside, and then this is already written in standard form. So I'm going to do 2, 1, negative 5, and 2. So 2, 1, negative 5, and 2. I'm going to bring down the 2. 2 times 1 is positive 2. I'm going to add 1 plus 2 is 3. 3 times 1 is 3. I'm going to add negative 5 and 3 and get negative 2. Negative 2 times 1 is negative 2, which adds to 0. Since the remainder is 0, x equals 1 is a 0. According to the factor theorem, we can plug x equals 1 into the function, and it should also be 0. So f of 1 equals 2, 1 cubed, plus 1 squared, minus 5 times 1, plus 2. 2 times 1, plus 1, minus 5, plus 2. 3 minus 5 plus 2, negative 2 plus 2, 0. Since we plug 1 into the function and we get 0, and we did synthetic division, and the remainder was 0, we have confirmed using the factor theorem and used synthetic division to show that x equals 1 is a 0. To determine if a polynomial has a specific remainder, we can use synthetic division. So since we're dividing this polynomial by x divided by 2, we put negative 2 on the outside of the synthetic division, and we use our coefficients. So we have 3, 8, 5, and negative 7. Now we'll do our synthetic division. We bring down the 3. 3 times negative 2 is negative 6. 8 plus negative 6 is 2. 2 times negative 2 is negative 4. 5 plus negative 4 is 1. 1 times negative 2 is negative 2. Negative 7 plus negative 2 is negative 9. We can see that our remainder is negative 9 by doing synthetic division. Now we can confirm using the remainder theorem by plugging in negative 2 into the function. If we plug negative 2 into the function and it is also negative 9, we've confirmed that the remainder theorem works. So we have f of negative 2 equals 3 times negative 2 cubed plus 8 times negative 2 squared plus 5 times negative 2 minus 7. So we have 3 times negative 8 plus 8 times 4 plus negative 10 minus 7. So 3 times negative 8 is negative 24. 8 times 4 is positive 32 minus 10 minus 7. When we simplify, negative 24 plus 32 is 8 minus 10 minus 7 minus 2 minus 7, which is minus 9. Plugging f of 2 in, we also get negative 9. We've now confirmed our observation that the remainder is negative 9 by using the remainder theorem.